Good morning, colleagues, academics, and community. Welcome to the second day of activities at the CBI Meeting 2024. To start our day right, we have the participation of an exceptional guest, Professor Mikhail Tkachenko. Professor Mikhail Tkachenko was born in the former URSS. He received his PhD in mathematics from Moscow State University in 1981. He worked as a professor at several higher education institutions in the USSR. In 1993, he obtained a patrimonial position from CONACYT in Mexico, and since then, he has worked as a professor researcher at WAMI. Since 1998, he has been a member of SNI Level 3, and recently he has been appointed an emeritus researcher. He has published 2 scientific books and around 218 research papers in international journals with a strict referring process. He has been the advisor for 6 PhD and 6 master's students. Several more are about to graduate. He has presented about 54 invited lectures at national and international topology conferences. He has carried out around 32 research leaps in Australia, Brazil, China, Spain, Japan, Israel, Poland, and Czech Republic. He has held several academic administrative positions at WAMI, and well, his research interests are topological structure of different objects in topological algebra, topological groups, paratopological groups, linear spaces, etc., cardinal invariants of topological spaces and topological groups, special types of orders in topological spaces, generalizations of compact spaces, pseudo-compact spaces, countably compact spaces, Lindelof spaces, dimension theory of topological groups, free topological groups, and maximal, submaximal, and unsolvable spaces. Today, we have the pleasure of hearing his talk in the topological game, Who Wins? Thank you, Professor Tkachenko. Anytime you like.
No? Thank you for the presentation. It's my honor to be here and present a talk, but I expected there would be a blackboard to write down something. So I see it's a little bit difficult there. Okay, so then I will try to explain everything by fingers. Well, okay, so I see some students of mine, or just some other students from topology, so that will make my task a little bit easier to explain the things. So the concept, or the main topic of my talk, is about topological games. So those games are infinite in nature, so each of the two players makes infinitely many moves. Well, the first, then the second, then again the first and the second, and there are many topological games. All are infinite. What are they for? Well, usually we try to characterize some properties of spaces. Sometimes those properties are very difficult to express in usual terms, just using the well-known properties like compactness, Lindelofness, etc., etc. So, you know, the world is much more complicated than we think about it, yeah? So, topological games are a kind of instrument that enables us to tackle with quite complicated issues related with topological spaces. And there are many topological games because there are many topological properties. So I will tell you about just one game, which characterizes very nicely some very simple topological properties. And this game is the so-called point open game. There are many point open games when one person, the first one, choose a point, the second choose a neighborhood, open neighborhood of that point. And then once again, the first chooses a point, the second chooses a neighborhood of the second point. And so they move around. And now the crucial point is just to say who wins. Yeah? So there are many different ways to define the winner. And one of the variants of this game would to say that the second who chooses neighborhoods, he wins if he covers the whole space. So you can game in any space, topological space. So the game depends on the space, of course. Yeah. Well, so the goal of the second player who chooses neighborhoods is just to cover. Not to cover the space. This is the goal of the first player who chooses point. So the second one who chooses neighborhood, he don't want to cover the whole space. So he wants to choose small neighborhoods of the point. So the first one wins if the second one covers the whole thing. If he not, the first wins. Okay? So we have everything. And the game is the so-called game with complete information. What does it mean? It simply means that both players knows perfectly well all the moves they have done up to the moment. Fine. So let's start the game with something very simple. The closed unit interval, 0, 1. Okay? So you don't need to know any topology for that. Yeah? That's the nice thing. Because our open sets are just open intervals. AB, open interval, without endpoints. Okay? So, no topology. Fine. So, the question is, who wins? So, once again, the first person chooses a point, the second, open interval containing a point, and then continue infinitely many times. And finally, we take the union of all open intervals, and if they cover the whole interval, then, well, The first one, 1. Okay? So, the question, who wins? What do you think? Your opinion? Who? The first or the second? Guess, please. Or we can start gamble. Well, if you don't have suspicions, then I give you an answer. The second wins in every game, in every possible game, because the second one has a winning strategy. What is a winning strategy? Well, I won't, of course, I don't have any mean to explain this in whole detail, because a winning strategy is a function depending on all the previous moves, yeah? But in usual human terms, it's just a kind of possibilities to choose all those open intervals so small that they won't cover the interval, yeah? For the second player. So let's think how we can do it. Look, the whole interval has the length 1. So if the second chooses the first interval of length less than 1/2, the second one less than 1/4, the third one less than 1/8, then you know the sum of these numbers is just 1. But the second one chooses something smaller, yeah? So the sum will be less than 1. So those intervals won't cover the interval of length 1. And that's it, yeah? So very simple, yeah, strategy, yeah? Just take small intervals, nothing else, okay? Fine. So it's simple. Now, let's go to take another space, the so-called counter set. Well, counter set is a very good example of a compact space. Well, the closed unit interval, of course, is a compact space, yeah? You know, the Heine-Borel theorem, yeah? Well, so let's take the counter set. What's the counter set? The counter set is a set obtained by taking away from the closed unit interval many open intervals. You divide in 3 equal parts and take away the middle. Then you have 2 intervals that are left when you take away the first part. You take again the middle thirds in the 2 intervals, take them away, and now you have 4 small intervals. Again, and you proceed the same thing, taking away those intervals, middle thirds, yeah? Fine. So finally what you will get, it's the counter set. The counter set. It's closed because you take away open intervals, and the union of open intervals is an open set. You take away an open set, you have a closed set. And that's it, a compact space. And it's huge. Again, it has the cardinality of continuum. Yeah? So it's B, but it's closed, it's compact. And now, the problem is that its Lebesgue measure is 0, because all those intervals you take away has length equal to 1. So it's very small by measure. Fine. So, who wins? It's the same game. You take open neighborhoods which just open balls. You take the usual metric, the absolute value of the difference, no? And takes an open interval of some radius, epsilon, no? In each step. So those open neighborhoods of points. Or if you know topology, then that just take open neighborhoods in the relative topology, yeah, of the counter set. So who wins in this game, in the counter set? Now you can speculate on the measure, yeah? Yeah, the second. Again the second. Why? What happens? Why I gain the seconds? Well, there is a good reason for that. The reason is that there is a continuous mapping of the counter set onto the closed unit interval. Well, it's a good exercise, and my students know it, yeah? We did it the last class, yeah? Last course. So there is a continuous function from the counter set over the closed unit interval. And now the strategy is clear. What the second must do, the second player? Well, just thinking that he games not in the counter set, but in the closed interval using this function. And choosing a closed open intervals of the images of the points. The first chooses the points in the counter set, but the function, our continuous function, maps the counter set on the closed interval. So you take open intervals not in the counter set, but in the closed unit interval, and of the images of the points. Then you three images. Compact spaces is something. It doesn't work. Okay, fine, thank you. So I will continue to explain something only for compact spaces because they are much better, yeah? So the next question will be, okay, so the second player wins, no? In these spaces like closed interval, a counter set. But are there spaces when the first one wins? Of course, the answer is yes. Countable spaces. Just countable. So the first player just enumerates the space, x1, x2, x3, and the next move, he just chooses point xn. And the second one must take an open neighborhood. So he chooses in particular the point xn. So the second will cover everything. Yeah, so it's not a problem at all. Yeah, fine. Thank you. That will help. So for countable spaces, there is no problem. The first one will win in the game with very simple strategy. But something more complicated? Well, something compact, which is uncountable. So just to exclude this simple and trivial possibility to win, well, so the answer, yes. There is a very good class where the first one win, and we can characterize those compact spaces where the first one wins. Thank you. Okay, I'll put it here. Thank you a lot.
You're welcome.
Well, so what are the spaces I mean? They are called scattered spaces, or in another terminology, dispersed spaces. What are the definitions? The definition for topologies is absolutely simple. A space is scattered or dispersed if every non-empty subset has an isolated point. And that's it. Very simple. Okay. What is something special about those spaces? The thing is that those spaces can be well ordered. So X is a space, and if it's scattered, we can find a well order such that this space will have this special property. So all points in this space which are less than a given one, X, is open in X. for each point. So how one do it? Very simple. Look, the space is B. So we take all isolated points. It will be the first level. And we will load it. You know, it's a well-known thing. Every set can be well-loaded, given a well-order. So you take this first level, all isolated points, you take them away, and you have a rest. But this rest, if it's non-empty, it has an isolated point. So once again, we take all isolated points in the rest, and we add after the first level. So it goes after. Then we take the third one, taking away the first and the second, and continue until the rest is empty. Okay? And you can easily verify that it's exactly you need. Yeah? So all initial segments will be open in this order. Well, so now we want to play in a scattered space, a compact scattered space. So who wins? Well, I said you, the first one. Independently how big the space is, yeah? Compact. So in a compact scattered space. So first wins. The first player will always win. So what is the strategy? The strategy is the following one. Look, the space is compact. And if it's compact, it has the maximal point. Look, the thing is very simple. Each initial segment is open. So you just take all initial segments, and if the space has no maximal element, all the segments will cover it. And the cover won't have a finite subcover. If the space doesn't have a maximal element. So it's not compact. So if it's compact, it must have a maximal element. So the strategy for the first player will take the first move, the maximal point. Then the second must take an open neighborhood of this point, yeah? Then the first one takes the rest, the complement to the chosen open set. It will again be a compact space because we take away open, it's closed, so it's compact, and again it will have the maximum point. So the second move of the first player will be that maximum point. And so on and so forth. And he will win. Why? It's not clever. But look, it's very easy. The set is well ordered. So by definition, it means that every non-empty subset has a minimal element. Okay? So let's write the choices of the first player. X1, X2 at the second step, X3, and so on. But what is the property of this sequence? Well, they go down. Because you take away not only the point, but also an open neighborhood containing the point. So the next one is less, etc., etc. So you obtain an infinite, strictly decreasing sequence, but it's not impossible because this sequence has no minimal element, but our set is well ordered. So every set, subset, non-empty subset must have a minimal element. So at finitely many steps, the second one will cover the whole space. Otherwise, we have an infinite decreasing sequence. So that's very simple. Yeah, you see? Well, so now the question. Let's take any compact space. Any. Uncountable. Well, just to exclude this trivial situation where the first one wins because of the countability. Who will win in an arbitrary space, compact space? So we have closed unit interval, counter set, well, dispersed compact spaces. So you'll see sometimes the first one wins in this space, in compact scattered spaces. Sometimes the second one wins, like, well, closed unit interval and counter set. So what is the answer? Take any compact space. What will happen with it? Topologists? What is? Well, okay, again, I give you the answer. The answer depends if you can map a space. So we have any space X, but compact. And imagine you can map it by a continuous map onto a closed unit interval. And now you know what to do, yeah? Just game in this one, yeah? And choose open sets here, and then take the pre-images. Just the same thing we did with counter set. Yeah? So if there is a map of our space onto the closed unit interval, the second player wins. The same trick. Yeah? Well, so if we have such a continuous map, the second one wins. Okay, but if we don't have such a map, then the space is scattered. This is a theorem. Probably somebody of topologists know it, yeah? So the thing is really simple. If there doesn't exist such a mapping, the space is scattered. And then the first one wins. So our game characterizes scattered spaces. If we want for the second to win, then the space, compact space, must be scattered. And that's exactly the whole story for this game. But there are many other games which are, well, more tricky than this one. But of course, this is not, I have not finished the game because there are non-compact spaces. And there, in non-compact spaces, the situation is more complicated. So I just explained you everything about compact spaces. In the non-compact spaces, there are some subtle things, and probably even bizarre things, yeah? Depending on, even on axioms, no? Because, well, you know, some assertions in set theory, and topology is very close to set theory, many hypotheses, the answers to hypotheses depend on set theory, yeah? They are, well, independent on the usual axioms, etc., etc. I don't want to enter those subtle things because, well, it's tricky. It depends on logic, on set theory, but, well, but for compact spaces, everything is okay. You see it, yeah? Well, okay, so this is exactly was my goal to present today. Thank you for your attention. Y ya pasamos al español, ¿no?
Yep. Okay. Thank you, Professor Tkachenko. It's been an honor. If you have any questions, please.
But still, it has to do with a winning strategy. I mean, if the first or second player tries another strategy, he may lose.
Yeah, but that will be a losing strategy.
Certainly.
Usually we try our best, yeah? Okay, but it's another point of view.
Any other questions? No?
Probably you have one.
Well, if somebody asks a good question, we have a present. So come on.
What if we have a third player?
Ah, well. But then it won't be topology. Probably it will be economy. You know, multiplayer games. Usually they occur in economy, no? Cooperative games, you know, or games with opposite interests. It depends. But usually in topology, we have just two players. You know, Bob and Elise. Yeah? But that's because of Einstein. Yeah? Einstein and the company, they invented the games, but in physics and quantum mechanics. But, well, we adopted the names, nothing else. But only two.
Another question?
Sorry, if you relax compactness, for instance, Lindelof or, I don't know.
Lindelofness.
Lindelofness.
To be honest, I did not think about it.
Because it has to do still with countably things.
Yeah, that's a very natural thing, of course. Yeah, even for subsets of the real line, it makes sense because they automatically Lindelof, all the subsets. Huh? So I guess, my guess is that there will be even subspaces of the real line where you can define who wins. The so-called undefined game, and depends on the space. So if the space is some kind of complicated one, you cannot have, probably no one knows the first one, nor the second one will have a winning strategy. So it will be just will depend on how they move. But the strategy, it can not exist at all. So that's the complexity of the situation. So the structure of a space somehow can guarantee you the existence of a winning strategy for one of the players. But the same structure of a more complicated space can just tell you that no, you can't have it, not for the first one, nor for the second. It's my guess.
Okay. Well, well, I think yeah. So much. Does anybody has any? Oh, another question.
Yes.
Okay, thank you. Do you want to make your question? Yeah. Okay. Sorry.
Okay. What do you think is the best contribution of topology today, since we currently use these tools in quantum mechanics and relativity, special and general relativity?
Well, you would probably better ask my son about those applications. I only know about applications of topology for, well, there were two Russian guys in London. They gained a Nobel Prize in physics, applying some topological methods in nanotubes, constructing of nanotubes. Well, my son does quantum physics, well, professionally, for a long, long time. So he knows better.
Yes.
But that's one of the examples of a, but this is not the kind of topology they do. It's a differential topology. I do general topology and topological algebra. You know, the world of topology is almost infinite, like topological games. There are many different branches of topology. And my topology doesn't have any applications, well, except for functional analysis, etc., etc. Yes, they have many perfect applications, very subtle, but this is inside of theoretical mathematics. In physics, they do differential topology sometimes.
Okay, and that maybe that sounds crazy, but in the medical industry, there are contribution. There are contribution that topology or exist a contribution in the medical industry. Yes. Or
Yes,
no?
yes. Again, you can ask my son, because he does it, applying quantum mechanics. For example, aspirin, as far as I know from him, there are two very close semi-stable states of aspirin. So if you don't buy it immediately after production, during some period of time, he moves to another semi-stable. And then it won't work as you expect. So he wrote an article about, well, etc., etc. So how they study? They have some functions describing the level of energy and try to modify the surfaces. Well, you have some layers of atoms, no? And you move one layer with respect to another, you try to determine where the local minimum and local maximum. Yeah? Okay. And this is a very difficult thing, because those local minima and local maxima are very non-pronounced. I mean, very slow. You can define just in a very small region, you see. They're not like this one, yeah? Maximum, yeah? Very simple one. They're very, very, very subtle things. So there can be very many of them. So it's the study of those quantum functions is a very difficult stuff. But if you have a very good method of computing, then you can save tons of money producing medicine.
Okay.
So this one of the things my son also does. It has something with topology, because the methods are quite complicated, and some of them involve some kind of differential topology and other combinatorial topology, etc. So there are many topology branches.
Thanks.
And one of them, yes, you can apply in medicine. Well, and you can then gain tons of money, if you like it.
Okay, thank you very much, Professor. We want to give you some appreciation gift. So if you want to take it.
Thank you. Thank you a lot.
Also these ones. Yeah.
Thank you. You're very kind.
Thank you so much. Please thank Dr. Kachenko for his participation.
Thanks for watching.
Yeah, it's for him.